Moving on with our unit of circular motion and field forces, we're now going to discuss the first of two field forces that we're going to cover in AP Physics 1. And we've talked about the gravitational force before, otherwise known as weight, because here near the surface of a planet, we can find it pretty easily by just multiplying the mass of an object by the acceleration due to gravity here at the surface of Earth, which is approximately 10 meters per second squared. Pretty straightforward. But now we're going to start talking about gravity in much more detail. And we're going to do that by first covering Newton's universal law of gravitation, as well as the concept of gravitational fields. Well, we've already discussed that all masses, specifically all gravitational masses, exert gravitational forces on other masses. So what is really going to affect the size of those forces? Well, first off, this is kind of the situation I have. I have two masses here, whatever they may be, m1 and m2, and r, this line here, is really just the distance from the center of one mass to the center of the other, so showing how far apart they are. Well, we can probably already guess that if we have bigger masses, we're going to have a bigger gravitational force. So the masses, each respective mass, is directly proportional to the size of that gravitational force that these two masses are going to exert on each other. Additionally, we probably have an idea that if we move the masses further apart, well, that gravitational force is going to be weaker. So we would say that the distance is inversely proportional to the gravitational force. But this is not quite accurate. It is true that as you get them further apart, the gravitational force goes down, but it's actually not a 1 over r relation. Instead, what it actually is 1 over r squared. Meaning that the gravitational force is inversely proportional to the square of the distance, something known as an inverse square law. And we're going to see another one of those later in this unit. Now, this was all formulated into one single proportion by Isaac Newton in 1687, that the gravitational force was directly proportional to the product of the two masses, so just multiply them together, over r squared. So this is really what Isaac Newton essentially put together, really from experimental observations for the most part, which was that the gravitational force was directly proportional to the product of the two masses, inversely proportional to the square of the distance separating them. However, this is just a proportionality. And if I have a proportionality, that means this times some number will equal that. So ultimately, if we want to get an equal sign here, we need to multiply one side of the equation by some constant. But we don't know what that constant is, and Newton didn't know either. In fact, that constant was not discovered for at least 50, 60, 70 years after his death. Specifically, by another Englishman named Henry Cavendish, and was found in the Cavendish experiment. And ultimately what Cavendish did was, this is something known as a torsion balance. And basically, that's a real fancy name for saying we have essentially like a rope here. We have a wooden rod, and on each end of the wooden rod, we have two really heavy lead balls. And then essentially all Henry Cavendish did was he put smaller lead balls near the two big ones and just saw how much this whole system began to rotate as literally the gravity of these balls attracted each other. And in doing that, he was able to figure out the exact constant of what should be going here, which is something that we call G, the gravitational constant. So now we have the true equation for Newton's law of universal gravitation, which is that Fg is equal to big G m1 m2 over r squared, where Fg is the gravitational force between these two objects, 1 and 2, in newtons. G is a gravitational constant, get there in a second. M1 and M2 is the respective masses of each object, so in kilograms. And R is the separation distance between the two in meters. Be very, very careful. R is not a radius, it is a distance. And that is something that people often make a mistake with. First off, let's talk about what this gravitational constant is. This gravitational constant, which is on your equation sheet, but you should probably put in your notes because you're going to have to refer to it a lot, is 6.67 times 10 to the negative 11 newtons times meter squared per coulomb squared. Now, a couple of key details here. First off, object 1 and object 2 are really specifically supposed to be point masses, which means that either one, they need to be spherical, so like a planet or a moon or something like that, or they need to be so far apart that their proportions don't really matter. So if you're looking at yourself and another human, you would need to be far enough away that we could approximate you as though you were a point or a sphere, and then you'd be okay. But this is the distance between the centers of these masses. So if I've got like the Earth and the Moon, the distance has to go from the center of the Earth to its surface, the distance between, and between the surface of the Moon and its center. That would be the total R there. Additionally, the direction of the force is always toward the other mass. So that makes sense. Gravity is always attractive. So one is towards one mass, the other is towards the other mass. And additionally, this is the force of gravity on each of the two objects because they make up a force pair. Object 1 applies a gravitational force to Object 2. Object 2 applies the same gravitational force in the opposite direction on Object 1. So let's go ahead and do a little bit of practice here. I want you to go ahead and determine the gravitational force between these two bowling balls, which are spherical masses. That's pretty acceptable. So one is 7 kilograms, one's 5.5 kilograms, and their centers are 2.5 meters apart. Go ahead and pause the video. I want you to try this on your own and then come back and see how you did. Hopefully you gave it a shot, but let's see exactly how we can determine that gravitational force. Well, we're going to use Newton's universal law of gravitation, g m1 m2 over r squared, and we're going to substitute all of our values. So g is 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared. Each mass is 7 kilograms and 5.5 kilograms over 2.5 meters. And be very, very careful. Everyone forgets the squared. So make sure you remember to square that distance. Stick that in your calculator. Don't expect you to do that in your head. And we're going to get 4.1 times 10 to the negative 10 newtons toward each other, which you'll notice is an incredibly tiny number. And that is because, compared to pretty much every other force, gravity is actually extremely weak. Compared to pretty much every other force we talk about, it is incredibly easy to overcome the force of gravity. You can do it yourself by literally just jumping off the ground. So the important thing here is that the reason why it is so small, if we look at this constant. It's times 10 to the minus 11. That's incredibly tiny. So you really don't notice gravitational forces until we start getting gargantuan masses. Typically speaking, we're going to be dealing with planets, moons, asteroids, the sun. Those are going to be the type of masses that we will look at, astronomical masses, in which case the gravitational force is pretty easy to see. But this leads to a question that we've kind of ignored, which is that the masses don't have to touch each other to exert gravitational forces. It's not a contact force. And how is that possible? Well, let's kind of think through this for a second. Let's say we have some big mass, m, so capital M is still just a symbol for mass, just using that to think of a big mass. And let's say I go to some point in empty space really far away from the Earth here. Well, if I do that, what exactly is happening there? Well, if I put another piece of mass, a smaller piece of mass, which I label little m there, well then we know that they're going to exert gravitational forces on each other. That the big mass is going to pull the little mass with Fg, and the little mass is going to pull the Earth with Fg. But the question is, if we don't have that there, is there something still happening here? And the answer is yes. There is something here known as the gravitational field, generated by this big mass. It is literally inside of that empty space, and in fact surrounds the Earth and all the empty space around it. The gravitational field, which we typically abbreviate with a little g, is a 3D physical alteration of space created by a mass that causes other masses to experience gravitational forces. Okay, so let's think back to that previous situation. In other words, that big mass, the Earth, physically, because it has mass, physically alters all of physical space and causes all other masses to experience gravitational forces due to the manipulation of literal space. And when I say space, I don't mean outer space, I mean physical space around us. Now, the gravitational field is a vector. But what does the strength of that gravitational field depend on? How strong is it? How big is that field? How much does it manipulate the space? Well, first off, it depends on how big this mass is. So if I have the mass of the Earth, it manipulates space quite a bit. If I have a smaller piece of mass, it does not create nearly as strong of a gravitational field. But it also depends on the distance from the center of that object. So this distance r here, going from the center of the Earth to some point, if we go further and further and further out, the manipulation of space is going to be less, and the gravitational force will therefore be less. Additionally, the direction of the gravitational field is always towards the mass generating the field. So that's what all these vectors are showing here, is that they are always pointed towards the mass generating the field, which in this case is the big M, the mass of the Earth. So as we're nearby, really big, gravitational field, as you get further out, those vectors decrease in size because it is weaker. Now, something important to note here is that since it depends on only the mass generating the field and the distance, what that tells me is the gravitational field here does not get affected by whatever we place there. If we put any other mass there, whether it's a human, a satellite, an asteroid, a planet, whatever, everything would experience the same gravitational field there. Now, the gravitational forces would be different, but the gravitational field, which is only dependent on this big mass generating it, would be the same. This is a very bizarre concept. Field forces. Now let's go back to review them for just a second. That these are any force that does not require contact. So they can, we say, act over a distance. The four that we really encounter are the gravitational force, the electric force, the magnetic force, and our nuclear forces, the strong and weak force. Now, we're obviously going to be focused on the gravitational one right now, but this is very, very weird. It's almost kind of ghostly. And this really bothered Newton. Newton was able to explain how objects affected each other with gravity, but he really couldn't explain the why, and that really, really bothered him. And he kind of just left it as a, we don't know now. All field forces are created by fields. Okay, well, what is a field? A field is this manipulation of space that is generated by a piece of matter possessing some fundamental property. Mass, charge, whatever. The field physically alters the space around this piece of matter and applies forces to other pieces of matter inside the field with specific fundamental properties. Okay, that was a lot. So let's kind of review what that means in the context of gravitational force. So to kind of translate this, a gravitational field is generated by a piece of matter possessing the fundamental property known as gravitational mass. The gravitational field physically alters the space around this piece of matter and applies gravitational forces to other pieces of matter inside the field with mass. Now, the strength of any field, whatever it may be, can be determined by dividing the force the field exerts on another object by the specific property that the field is interacting with. Okay, once again, it's kind of a lot of gobbledygook. So how can we make that into a more translatable sentence? Well, ultimately, what this is telling me is that the strength of the gravitational field, which we abbreviate with this little g, is equal to the gravitational force on some piece of mass in the field divided by the mass of that object, which is what the field is interacting with. So looking at this picture here, if I'm looking at the Earth, for instance, I'm at some point out in space, the gravitational field of the Earth at that point would be equal to the gravitational force it exerts on the specific object divided by the mass of that specific object. So let's go ahead and take this a step further that we've already talked about. Well, we can calculate the gravitational force using Newton's universal law of gravitation. So for Fg, I stick in g mm over r squared. Now note, I used m and m now. This is really the same thing as m1 and m2. m1, m2, big M, little m means the same thing. I'm using big M and little m here to be very, very clear about which masses I'm talking about. Specifically, m is the big mass generating the field. M is the little mass placed in the field. Well, if we look at this now, g and m and r squared, they're all good, but the little m's cancel out. And what I really end up with is g big M over r squared. And in fact, this is the equation for the gravitational field strength. So we have really two different forms of it. That the gravitational field strength, which note, is in newtons per kilogram. We're going to get there in just a second. So newtons per kilogram is equal to the gravitational force on an object in newtons over the mass placed in the field. little m is the mass put in the field in kilograms. Equally, it is also equal to the gravitational constant, 6.67 times 10 to the minus 11, times the mass generating the field in kilograms over r squared, which r is the distance from the center of this big M to some point in space in meters. Remember the squared. So one thing I want to really key in on here is this newtons per kilogram concept. What that's telling me is, like, let's say G at this point, I'm going to make up a number here, is 2 newtons per kilogram towards the center of the Earth. So what that tells me is if G is 2 newtons per kilogram there, if I place an object there of, let's say, 1 kilogram, the gravitational force would be 2 newtons. Similarly, let's say I put a 2 kilogram object there. If I put a 2 kilogram object there and the gravitational field strength is 2 newtons per kilogram, well, that would be 1 kilogram would be 2 newtons, 2 kilograms would be 4 newtons. That object would experience a gravitational force of 4 newtons. If I put in a 10 kilogram object there, well, that would be 10 kilograms, 2 newtons per kilogram. That would be experiencing 20 newtons of force towards the center. So the G does not change. What changes are the masses and the gravitational forces. So let's go ahead and look at an example, and you're welcome to try this again on your own if you'd like to. How strong is the gravitational field of the Earth near its surface? Okay, well that should be pretty easy to do, specifically because I'm going to give us this information that the mass of the Earth is 5.97 times 10 to the 24th kilograms, and if we're near the surface of the Earth, so right here, well then the distance from the center would just be the radius of the Earth, which typically if we're looking at the radius of a planet, we're going to use a big R, but same thing. So distance from the center, so the radius of the Earth is 6.37 times 10 to the 6 meters. So if I want to calculate the gravitational field strength, I just use the equation. G is equal to big G, big M over R squared. And I'm going to go ahead and plug in my numbers. 6.67 times 10 to the negative 11. The big mass is 5.97 times 10 to the 24th kilograms over 6.37 times 10 to the 6 meters. Remember the squared. Stick that in your calculator, and let's see what we get. Well, when we do that, we get 9.81 newtons per kilogram. So the gravitational field strength near the surface of the Earth is 9.81 newtons per kilogram. But that number is really, really familiar. Where do we know it from? Well, that's because we learned this way back in Unit 2. This number is in fact the acceleration due to gravity near the surface of the Earth. The gravitational field strength and the acceleration due to gravity are the same thing. That's where that number comes from. So if I find the gravitational field strength anywhere else at any other point in space, that's telling me the acceleration due to gravity at some other point in space. And this is really a result of the fact that gravitational mass and inertial mass are equivalent. Now, what couple things to note here. First off, well, that may sound weird because the units are different. You know, the units of gravitational field strength were newtons per kilogram, but a Newton, remember, it's just a mass times an acceleration. A force is a mass times acceleration. So it would be kilograms times meters per second squared over kilograms. They cancel the kilograms. Look at that. Meters per second squared. Those units are, in fact, identical. Additionally, this is why the acceleration due to gravity near the surface of the Earth, or really at any point, is the same for all objects. Because it only depends on the mass of the Earth and the distance from the center of the Earth. It does not depend on whatever object we put there. If you have a really big object that we put in the field, you know, like maybe a gigantic wrecking ball that you put in this field, well, it's going to experience a really strong gravitational force when it's near the surface of the Earth. But if I put something really tiny there instead, like a feather, what's going to experience a much smaller gravitational force. But when we divide those by each other, we're always going to get the same constant value, specifically of 9.81 newtons per kilogram, or 9.81 meters per second squared, near the surface of the Earth. So what are the main takeaways for this lesson on the law of universal gravitation and gravitational fields? Well, one, can we utilize Newton's law of universal gravitation to examine the factors that affect gravitational forces, the size of the two masses and the separation between them, and calculate said forces using the equation? Can we conceptually explain how masses exert gravitational forces on each other without touching, remembering that masses generate gravitational fields, and those gravitational fields exert forces on other masses. And lastly, can we calculate the strength of a gravitational field, otherwise known as the acceleration due to gravity, generated by a particular mass at some point in space?